Today we're on 3-6, which is called curve sketching. Guys, please make sure we have some new class policies, right? Third row. Hello, third row. No electronics out, please. Guys, hello, third row. No electronics, right? Remember the new policies? And so today we're on 3-6, and then Wednesday we're going to have, so the remainder of this week we have a presentation, kind of similar to the related rates thing we had last semester. Okay, so Wednesday is going to be a work day for that, and then Friday you guys have to give the presentation. I don't really know the parameters for that yet, but I'll try to let you guys know what Miss Lee does. Okay, not necessarily my idea, but it sounds fun. Okay, Barack? I think it's probably going to go in progress. Sorry. Any questions about that? The presentation on Friday. Wednesday will be a work day, and Friday will be a presentation.
What are we presenting?
Something about this lesson.
So you're going to tell us what?
Yeah. Progress is 10%.
Master's 35, right?
Master's 50.
50?
Yeah, it's been 50. Okay, let's talk about today's lecture, which is curve sketching. So basically, in the previous sections, we've been talking about, first derivative, increasing, decreasing, second derivative, concavity. And so we've all been doing that mathematically, so algebraically. And today we're going to be thinking about how we can apply what we know about a function algebraically and try to think about how we would draw the graph of it. Okay, and actually derivatives are pretty powerful in that they tell us a lot about the shape of a graph just based on the function. So it's probably most helpful to just do an example, and this will make it most clear. So the idea is we want to look for different information about a function and use that information to get the graph. And these are things that we want to, let's not do the example. These are things that we want to find out. It's not very good handwriting. What do we want to find out? We want to find out any asymptotes. Okay, so that's a good first step. So figure out whether it has any asymptotes. So we want to first maybe find vertical asymptotes. Right, vertical asymptotes are wherever the function has like a divide by zero error or something, We also want to figure out horizontal asymptotes. So if you guys recall from the last lecture, right after the quiz we had, horizontal asymptotes are like what the function approaches as x approaches infinity. So if we write it in limit form, we're interested, as x approaches positive or negative infinity, where does the function approach? Right, as x gets bigger and bigger, where is this function approaching? And if it approaches a certain number, then that's a horizontal asymptote. Right? And we thought about how the degree of the numerator and the denominator affects this asymptote, so hopefully you can refer to your notes to think about that. All right, there's a third kind of asymptote. Those are called slant asymptotes. Have you guys heard of these? Heard about it in algebra? No? Okay, so slant asymptotes are basically when a function doesn't approach a horizontal line, but rather a slanted line. So for example, I'll give you an example. If we had the function f of x equals x plus 1 over x, actually the graph is going to look something like this. It looks like this. Okay, and we say that it has a slant asymptote because as x approaches infinity, it doesn't approach a horizontal line, but actually a slant line. And what is this line? That's the line y equals x, right? And the reason why we know that it approaches y equals x is because as x approaches infinity, right, this 1 over x is going to start becoming really small. It's going to get really close to 0. And so as x becomes really big, really the only important behavior of the function is going to be the y equals x, because the 1 over x is going to be so negligible. That's what we call a slant asymptote. Okay, I'm very hungry. I don't know why. I ate a lot of... I'm good. Thank you. I don't like chocolate.
It's mostly that.
It's literally M&M's.
It's mostly that.
He's around that one.
You wait, before you... What if I
That was not my fault.
What's that hitting the head? Oh, my dream.
Let me continue.
You're the one who announced you were hungry. We'll try to help you.
Thank you, yeah. I said no thank you though. Yeah. Thank you.
Very respectful.
Yeah. Okay, we're also interested in intercepts. You guys know what intercepts are?
Yeah, when you intercept the line.
Sure. So we're interested in x-intercepts, which is where the function equals 0, right?
Yeah.
And we're also interested in y-intercepts, which is when the function, when you plug in 0 into the function, right? Right, y-intercept is where x equals 0, so you just plug in x equals 0, you can find the y-intercept. All right, so pretty easy so far. What else? Yeah.
So you always know the x-intercept, but you never know the y. That's
What?
you're saying. Like, as if you know f of x is always 0, then what's the point of like...
No, we're trying to figure out which values of x give us a function value of 0. And those are the x-intercepts, right? That's where it crosses the x-axis.
Oh, yeah.
Yeah. Okay, so we're also interested in, what are they called? Relative extrema. So, right, that means we have to find the first derivative and then find the critical values, and that will tell us the relative extrema, maximums and minimums. We also care about increasing and decreasing intervals. It is a lot of stuff. And then finally, we also want to find the points of, what are they called? Points of inflection. Points of inflection and concavity.
Oh, yeah, we did.
Right? We learned all of this. We learned how to find it. But now we're just trying to put everything together and figure out how we use this information to actually graph functions. It just takes quite a long time. But it's cool, you know? You don't have to use a calculator graph. You can just use your brain. Okay, any questions? Daniel?
What was the highest thing with this, like, grade?
Highest grade?
Yeah.
I don't know. I don't think anybody got 100, unless I'm mistaken. No. I'll curve it if Miss Lee curves it.
What would be exponential?
I just do whatever Miss Lee curves, and so she doesn't do the exponential curve. I like to do that though. Let's do an example. Let us do an example. I'll try to make it similar to what I have here. Let's say we have the function. Let me make it similar to part B. X over x squared minus 1, let's say. Okay? Let us be quiet. So to start, right, what is the first thing I want to find? I forgot what I wrote. Asymptotes. So to find asymptotes, it's probably best to factor the denominator first, right? So we can write it as x minus 1 times x plus 1. That's a difference of squares. So that tells us that we have two vertical asymptotes. One is at x equals 1, and one is at x equals negative 1.
X equals 0, because it would just be 0. So, but if it's 0 on the top, that on the bottom.
No, 0 divided by number is 0.
So would it not be 0 as well for a horizontal asymptote? Because it does 0 on the top.
The horizontal asymptote is 0.
Yeah.
Okay, the horizontal asymptote is 0, and why is that?
Because the one on the top, you plug in 0 in.
Actually, no. The reason is because the degree of the polynomial in the denominator is greater than the degree in the numerator. Okay, and so that means that the denominator gets bigger a lot faster than the numerator. Kind of what we talked about in 3-5, that very short lecture I did. Okay, so that tells us that the limit as x goes to infinity is 0. So that's the horizontal asymptote. What else do I care about? Let me actually draw these first, and so we can start setting some things up on our graph. Oh, the next thing was intercepts, right? All right, so here are my two vertical asymptotes, -1 and 1. And then I also have a horizontal asymptote at y = 0. I'm not going to draw that. All right, intercepts. Intercepts. Let's see. Where is the x-intercept? The x-intercept is wherever the function equals 0. And so that means the numerator has to equal 0, which means that the x-intercept is going to be 0, 0. Right? Because this function here only equals 0 if x equals 0. So that's pretty straightforward. The y-intercept is just plugging in x equals 0. So that's also going to give us 0, 0. And so we know that the graph must cross this point, right? That's its intercept. Okay? So that's all the preliminary information, and now we can probably start taking derivatives. I do not want to do this by hand, so let me use my computer. You guys have to use your hand though. Derivative of x. Okay, so the first derivative is going to be -x² + 1 over x² - 1 squared. Okay? And so now we're just going to do the same kind of process that we did on the quiz. We're going to figure out what the increasing and decreasing intervals are. Okay? I'm going to assume you guys know how to do that. So you first find all the critical points. It's going to have two critical points at -1 and 1. And so we do the same process of splitting it up into the number line, -1 and 1. And we do the whole process where we try to figure out on which intervals the derivatives are positive and negative. And we should find that we should have negative and then negative and negative again. Okay, so but all three intervals are all decreasing. Okay? And actually, based on this information alone, you are able to sketch the graph. Okay? Let me show you how. We know that all three intervals are decreasing, and we also know the horizontal asymptote. That is actually going to tell us that the graph will look like this. Okay, do you guys kind of see the logic? You have to think about where the horizontal asymptote is, and then think about how the function should behave if it's decreasing on every interval, and then also account for those vertical asymptotes where the function should increase to infinity or decrease to negative infinity. Okay, that's the tricky step, right? To go from all this information and to kind of infer what the graph should look like. But if you do the logic, it should make sense. It's kind of like a puzzle, right? Okay?
Wait, what's HA again? Sorry.
Horizontal asymptote.
Okay.
Let me just graph it to make sure I'm doing this right. Okay, correct. Horizontal asymptote, you have to figure out the limit as x approaches infinity. And so you're going to look at the degree of the numerator and the denominator.
Oh, right.
Yeah, so if the degree of the numerator is smaller than the degree of the denominator, it's going to be approaching 0. If it's the same, you do a fraction. And if it's greater, then it increases to infinity. Yeah, we learned that last class. Just there will be no horizontal asymptote if it goes to infinity.
So it's either 0, a fraction, or no?
Yeah, it's either going to be 0 or some number. It's only going to be non-zero the horizontal asymptote is only non-zero if the degree in the numerator and the denominator are the
So
same.
if it was like 2x squared, x squared.
Yeah, suppose this were 2x squared over x squared minus 1, the horizontal asymptote would be 2, because the degree is the same. Okay? So you'll notice that I did not find the points of inflection. I probably should have, but just didn't feel like it. But that will give you some more information about the graph, okay? And you would find that there was a point of inflection at x equals 0. Okay. How about you guys just go ahead and try it?
Copper?
Yeah. You guys know how to do everything. It's just the logic, right? That's the tricky part.
First step is get the horizontal